introduction, and let me begin by thanking Arnob and Pinaki for having me here. And this is my first visit to IMSC. I've been several times to IIT Chennai, but not here. So today I'll be discussing about some work that we are doing in our research group. So this is something which is, we are interested in looking into the phenomena called transition path dynamics, and we are looking into how it behaves in a rough potential barrier. And transition path times, I'll come to it, and I was introduced to this area long time ago during my postdoc time with Dima Makarov at UT Austin, and though I did not follow it up later, but we got interested into this again. So, in the context of barrier crossing rates or reaction rates, one of the most remarkable theory is the transition state theory, which is, all of you know, is based on the equilibrium formulation of chemical rates, where the reactions are known to proceed through a high energy intermediate called the transition state, which is assumed to be in equilibrium with the reactants. Then came the seminal work by Kramers, which kind of combines the rate theory with the theory of Brownian diffusion, where the dynamics of the molecule of interest is considered to be following Brownian motion, and the interaction of this molecule with the solvent give rise to a friction as well as to a random noise produced by the thermal motion. Now, when I talk about biomolecular rearrangements such as the protein folding phenomena between the folded and the unfolded states, they can be described by a two-state transition in a free energy landscape, where the two deep wells representing the folded and the unfolded conformer are separated by a high energy barrier. Now, in this barrier crossing phenomena, if we consider the reactant and the product states, then considering that the barrier height is much higher than the thermal energy, the particle will tend to spend most of its time in these local states, and then the quantity of interest is the first passage time, which is the time spent by the particle in one free energy minima before it makes a transition into another. So basically this barrier crossing event is essentially a rare event, as we can say, and the Kramers escape rate is obtained from the mean first passage time formalism. So in this whole thing, the time that is spent actually to cross the barrier is very small, and this is what we refer to the transition path time. This is a time taken to overcome the barrier region without recrossing the initial boundary. Now, these transit times are considered to be much smaller magnitudes than the first passage time. Now, one can actually look into this transit path times from simulations, but naive simulation techniques will actually not give us proper statistics because they are rare events, and one also needs to take care of the computational cost. So, quite some time ago, there were different single molecular experimental techniques that came into picture, which could give very good time resolution, and in this context, single molecule force spectroscopy measurements and single molecular FRET measurements were important, where in this kind of experiment a DNA hairpin was attached to two beads that are attached to optical traps under tension, and the displacement of the beads helps us to monitor the state of the molecule. As the unfolded form is considered to be in a more extended form than the folded one, by measuring the extension profiles, one can actually kind of find out what is the state of the molecule under interest. Similarly, there were single molecular FRET measurements where a biomolecule is attached to a donor acceptor pair, and depending upon the interfluorophore distance, the donor fluorophore will transmit energy to the acceptor fluorophore and light will be emitted. So, from the single molecular FRET measurements, one can calculate the FRET efficiency, which will describe the transition path from unfolded to folded states. So, these different studies have actually pushed temporal resolution to the microsecond time scale. If one needs to look into the dynamics of the system, to make life simple, one approximates that the reaction is a 1D barrier crossing problem and approximates that the top of barrier is a parabolic potential. And this barrier is symmetrically placed between minus x0 and plus x0. And since we are talking about transit paths where recrossing is forbidden, one needs to implement absorbing boundaries. Now, this is a basic idea of modeling, where we consider that the particle, the trajectory starts very close to the left boundary called as say minus x0 plus epsilon, and they are terminated when they reach x0, and ideally one has to put absorbing boundaries out here. And the easiest way or the most convenient way to start with is to use a overlap Langevin equation with a white noise and write down the corresponding Fokker-Planck equation. Now, the flux at the right boundary will essentially give us the trajectories that contribute to this distribution, and from the flux calculation one can calculate the transit path distribution. This is a basic idea, but this flux calculation requires us to get a solution of the Fokker-Planck equation, which is somehow not a very easy thing to do with absorbing boundaries in picture. One can do it for a linear or a free boundaries, free diffusion, but even for a inverted parabola, it is getting a solution with absorbing boundaries is not simple. So, what was done was open boundary conditions were used, and the analytical expressions for the transit path time was obtained. Well, here equation 49 refers to that expression, and what was found is that the agreements between the simulation and the theory became better for higher barrier heights, because analytically these results converged to absorbing boundary results in the high barrier limit where recrossing is extremely rare. Now, these theoretical results were used to fit the experimental data, and what was found is that the barrier height that one obtains by fitting the experimental data to the theoretical expression was an order of magnitude lower than free energy calculations from landscape measurements. And also these transition paths were only derived at the limit of diffusive dynamics, where friction is large and one needs to consider only the Smolnikowski limit of the dynamics. Now, based on all of these studies, there were certain open questions like, what are the effects of memory on the transition path distribution, transition time distribution? What is the transition path distribution when the friction is moderate or weak, that is not considering the overdamped dynamics? Whether considering a parabolic barrier is too simple a picture, and also what is the role of added dimensions in all of these cases. So, first and foremost, let me talk about the role of memory. Well, mapping a high dimensional system into an effective one-dimensional model essentially introduces memory effects leading to non-Markovian dynamics. So, in this case, due to the insufficient time scale separations due to solvent reorganization, the standard Markovian assumption kind of approximation fails down, and in that context one can actually do a non-Markovian generalization of the Kramer's model by using a generalized Langevin equation. Now, Heinz and co-workers have used this by where the frequency dependent memory friction coefficient had the memory effects, and their results were validated by Hangi and co-workers using the flux over population method, and later many simulation studies were done. So, there has been different other ways of treating memory in these kind of measurements of transit path distributions. For example, Pollock and co-workers have used a normal mode analysis where the particle is considered to be bilinearly coupled to a bath of harmonic oscillators. Makarov and co-workers have used a fractional Brownian motion model with an exponential memory kernel. Carlin and co-workers have used a generalized Langevin equation with a power law memory kernel. Well, power law memory kernel has been found to be very effective in describing dynamics of polymers and other systems with long relaxation time, and this study was done in the overdamped dynamics. Now, what was observed is that the inclusion of memory kind of broadens the distribution when the motion is subdiffusive, that is alpha is less than 1, and gives to a long tail distribution. And due to the strong correlation between the random forces of the thermal bath, the memory accelerates the transition path time. Though most of these studies till now have involved overlap dynamics, one thing that is important is that since transition time scales are referred to shorter time scales, we would kind of wanted to see is get an idea of the full distribution. That means what is the role of inertia, and that is what we did, where we included both memory and inertia in the picture. Low barriers, one would observe a difference between the transit path distribution obtained between absorbing boundaries and free boundaries, because recrossings can take place, and that is not what the transit path time is. And also, if one uses the distribution based on absorbing boundaries and fits experimental data, one will find that the transition path free boundary results as expected will converge to the absorbing boundaries. Well, in this case, the expression that was obtained by using this eigenfunction technique was also compared with using absorbing boundaries or by recrossing. Two types of potentials which will put through the results. Now, this yielded roughness needs to be considered for transition path analysis, and that is what we are kind of looking into. So, this is a potential that we use to include roughness, which is essentially an inverted parabola superimposed with an oscillatory cosine function. So, this kind of potential is something which is not very new, or the first time that we have used it. Here, this kind of potential have been used by Mesler and co-workers to study the memoryless dynamics under open boundary conditions. Here, epsilon refers to the amplitude of the roughness, and omega is a separation technique, and which actually allowed us to write the potential in the form of effective potential and the diffusion coefficient in the term of a effective diffusion coefficient, which led to the smoothing of the rough potential. And with this picture, we then implemented the eigenfunction diffusion. These are results using absorbing boundaries, and as we predicted, as we already discussed, that for a higher barrier heights, we will get very good fits between the open and the absorbing boundaries, but the open boundary can kind of overestimates the results for lower barrier heights. Now, we wanted to see how this transition path time depends upon epsilon and omega. So, we actually found that with increase in the amplitude of the roughness, the particle is kind of more stuck in the microstates along the transition path, that makes the distribution broader and shifts towards longer times. This is exactly what we see when we go on increasing epsilon. Also, one important thing in our model is that the value of the barrier frequency. So, this model kind of works for high values of omega. For low values of omega, the length scales are very large for the rough potential, as a result of which it will be not possible to approximate the total potential as only the parabolic potential. So this is also something that we found, that when omega is small, the fits are not so good. We also looked into another thing, that what is the effect of the barrier height. Well, when we think about a high barrier height, the inverted parabolic potential changes much faster than the rough part, as a result of which here also the superimpedance frequency, the separation of length scale, which is very important for this theory to work, separation between the roughness and the parabolic barrier, is difficult to attain, and in these two cases making spatial averaging less effective. So this is a result of the conditions, and found out the transition path distribution. These are exact results in the sense that by using a spatial averaging averaging technique. Now we wanted to see what happens when memory comes into picture. Say here the Fokker-Planck equation for a rough barrier, it is difficult to obtain the time dependent diffusion coefficient. So what we do is that we use a steady state flux analysis and we obtain a scaled time dependent diffusion coefficient. So this is how the scaled time dependent coefficient looks like, and so basically the problem of diffusion over a rough potential is kind of reduced to a diffusion over a smooth barrier with this modified diffusion coefficient. As before, I said that the scaling works better for lower values of epsilon and for lower barrier height, but what we see is that in the presence of memory, the random forces generated by the thermal bath are strongly correlated and facilitates barrier crossing. So this study, this particular exercise helps us to calculate the transit path distribution for a rough potential using absorbing boundaries by using this scaled time dependent diffusion coefficient. So if I want to conclude this part, is the conditions prevent is true when the length scale of roughness is very small compared to the length scale of the parabolic potential. So remember, the evaluation of this time dependent diffusion coefficient, the scale time dependent diffusion coefficient, requires one to use the steady state flux approach, and this has been numerically test barrier height. So I would like to mention here that this is kind of a limitation, that the roughness here, which has been addressed by scaling the diffusion coefficient, is a method that is valid for a highly corrugated potential with a low roughness barrier height. Also, we have applied this method. This method has actually requires a prior knowledge of a time dependent diffusion coefficient, which is known in the case of parabola. But for any other complicated shapes, it is kind of the potential, it is difficult to have a knowledge of this time dependent diffusion coefficient. Nevertheless, what we can say is that the role of roughness, which has not been kind of included much in the theoretical study of transit path times, we have tried to kind of look into that and see whether we can have some of the protein are known to be rugged and complex, which kind of lead to a broad spectrum of internal motion that are taking place on multiple time scales. Now, protein surfaces are not static, but they are considered to be plastic boundaries where they interact with ligands that lead to internal motion. These are known to explore different conformational spaces on functional time scales. For example, like in enzymes, one can see that the catalytic rates can exhibit significant fluctuations over time. And these internal motions can follow there's a power law behavior. So one can think that the dynamics of the folded proteins as a frictious particle executing anomalous diffusion on a rugged energy landscape possessing many wells of various depths, and the dynamics approach, or they have used the fractional Fokker-Planck equation approach. So, with the idea of roughness that we have for now, what we wanted to look into a particle confined in a harmonic potential with several microstate traps. And the idea is that for long time memory, the stochastic dynamics will be given by the fractional Fokker-Planck equation. So, I am not going to details where we go to the Fourier Laplace space, find out the solution, and from there we obtain the distribution and the moments of the distribution. These Fokker-Planck equations were essentially solved analytically under the assumption of small roughness value. Here A refers to the roughness parameter. And we wanted to go broader by looking not only restricted to this theory, but we wanted to do some simulation studies. And so, what we used is the continuous time random walk model, where we can actually characterize the behavior of a high dimensional landscape, and it provides us with the flexibility to look into a wide range of temporal correlations in subdiffusive dynamics, where it considers a power law waiting time. So, with these simulations, we actually calculated different statistical measures. For example, we looked into the mean square displacement and leads to a steady state. We actually also looked into what is the role of subdiffusive dynamics, and we compared at different values of alpha, and we see that with in the presence of subdiffusive dynamics, the strongly correlated motion kind of allows the particle to quickly reach the roughness minima, and the particle being trapped in the microstates, the plateau region dasticity or characteristic function. We looked into another quantity, which is the time average mean square displacement, which is very important in the context of single particle tracking, where we can look into the trajectory of the single molecule particle evaluated in terms of TMSD. These are simulation studies using the continuum time random walk model. And what we found is that roughness kind of leads to the prolonged trapping of the particle in the microstates, and that is the reason it kind of decreases the time average mean square displacement. We are also looking into what is the role of subdiffusion out here, and what we find is that for smaller alpha, long waiting times of power law behavior is encountered, which leads to the lowering of the TMSD. So, basically we can see that roughness with subdiffusion dynamics can lead to highly sluggish motion, thereby increasing the relaxation time in the harmonic potential. These are the different kind of statistical studies that we are doing. This is a work in progress. So, I think I will end here, and before I end, let me thank one of my PhD students, Pankaj, who is currently working in this project. I would like to thank ISA Pune, my SCRB CRG and SCRB Power grants for supporting me, and thank you all for your attention.
Questions? So, is there any general condition like the raptness or raggedness of the potential under which one would expect the Mittag-Leffler function or the correlation function versus say exponential or something like that?
See, Mittag, there are different ways people have used taken care of this kind of relaxation behavior as in taking Mittag-Leffler function, because they have been used very commonly to fit to experimental results. People have also used stretched exponential functions. So, there are different kind of contradicting or agreeing groups which believe that how good a Mittag-Leffler function is, and they have been mostly used for power law distribution. So, in our studies what we have done, we have used a Mittag-Leffler function and done it, but like I would not say that that's the only way to do it, since studies have been done by considering memory being more successful by using this power law distributions. That's the reason why we have also used the same thing.
Your analytical solution is Mittag-Leffler, or
Yeah, it's a Mittag-Leffler. It's a Mittag-Leffler. I didn't. It's a big form. It's a Mittag. No. It's the alpha value that we have used is 3/4.
3/4.
Yeah.
So in the Fokker-Planck equation with memory, you get an effective diffusion, time-dependent diffusion constant. So I just want to ask about the simulation. While you do the simulation, you run like you do the normal Langevin dynamics simulation with time-dependent diffusion constant.
Yes.
You do not simulate the
The
generalized.
simulation is not with an effective. It's a regular. We had to consider a scale diffusion coefficient only for our analytical work. Okay.
You do the simulation with the GLE starting from GLE.
Yes. Yeah. And that is what we found that you will who have done the analytical work using the scale diffusion, and the GLE the simulations are with just solving the GLE. So there are certain cases which I said that this analytical picture which we talk about, this length scale separation technique that works at certain conditions. That is why at certain places you see deviation between simulation and theory. Okay.
So for the transition time, you have to set this epsilon going to 0, right?
Yes.
How do you do it in a simulation? Like in the simulation, what is the value you put?
We did not need to do that in the simulations. We just solved the Langevin equation and got it. This was something that we did it in the analytical work.
But in the simulation, when you run the Langevin equation,
Epsilon tends to 0, right?
yeah.
So it's a very small value, right? It's just a small thing. Yeah, you can do that. We can discuss on this. I can tell you. Yeah, how to do.
Thanks.
So other questions? So I have a question. So you use this free boundary approximation. So what is that actually?
It assumes that it is just a solution of a Fokker-Planck equation, which does not consider that in the case of
But
a
you require the absorbing boundaries on the two
you
sides.
it is not even for a inverted parabola, it is not it is not known, right, the actual form of the solution of the Fokker-Planck equation with
So this free boundary in both sides, or one side you have a absorbing boundary, the other side is
absorbing,
free?
reflecting, absorbing boundary kind
So
of
one
solution.
side it's
Yeah.
reflecting, other side
Yeah,
is
absorbing
absorbing,
boundary.
not free.
Yeah, but not both sides are not absorbing.
So one
But
side is reflecting.
in
other side is-
transition, but in transition path, actual theory tells that it should be two-side absorbing boundaries, right? So that is where we have to look for the solution separately. Okay.
Okay. So if there are no further question, then let's thanks Ravanti once again. So our next speaker is Argho Dash. He's going to talk about, Argho is from Mad Science, and he is going to talk about boundary layers and universal distributions in boundary driven active systems.
Yeah, I thank the organizers for arranging this conference and giving me a scope to talk about some recent results on boundary driven processes. This is a recent work I have done and actually been doing with Pritha. She is in NIT Surathkal, and this is recently put to archive. So, the model is as I just mentioned, it is a boundary driven active. We have been listening as it happens for active process. Here we are considering this run and tumble dynamics, where in one dimension where the particle has a preferred direction of motion and with some certain rate its properties in the steady state, what will be the transport properties and what are say the long time distribution and the relaxed behavior. So, completely non-equilibrium statistical physics characterization we are looking for. So, to characterize this kind of system, usually we try to find the distribution of the particles at different times. So, here the particles come with two internal states, one it's so two states you just randomly assign one to be plus and one to be minus. In one day it can move in one direction and the other direction. So, you call it p plus and p minus, and if you somehow know this vector at different times, so you have the answer. So, we are aiming for that, and for this you solve this master equation with this boundary condition, and once you evaluate this p plus p minus separately, you can calculate the total density and total magnetization. So, this is the standard protocol, and we start by asking what are the steady state properties. So, this is a boundary driven system. So, we expect that for boundary reservoirs with two different densities, there will be also be a current. So, it will also have a transport behavior. So, we ask what is the steady state and transport. So, the equations I have just shown, in the steady state the left hand side is 0 and it can be quite easily solved, and you get a solution. So, this is the current. So, in this case first we consider that the boundary reservoirs, they provide only non-zero density. Although these are active reservoirs, it is giving in active particles, still first we assume that the magnetization of the boundary is 0. We will later see that what is the effect of non-zero boundary magnetization. So, with this boundary magnetization, the current is very much like a diffusive current. It depends on the density difference of the two boundaries. There is this well known effective diffusivity, and it is divided by the length, which is slightly modified by a constant. So, for large system size it is effectively a diffusive current. So, very much like passive. So, not much of a difference apparently. If you look at the distribution and magnetization profile, this is the distribution. So, two reservoirs, they are throwing in particles and particles also getting absorbed into the reservoir. So, apparently this is not really linear profile as we usually get, but this is for a small system. If you do a large system, take a large system limit, then you find that this is actually linear in the bulk, and this non-linearities come at the boundaries. This mu, this is a something of order 1, it is a length scale, mu inverse is a length scale, and you form a boundary layer. So, in active process boundary layer is known. For example, when the particle is moving in a reflecting within a reflecting barrier, so at the walls there is a boundary layer is formed, but here we see that even when there is this open boundary condition, a boundary layer is there, but still in the bulk it is largely diffusive, and the non-trivial or maybe you say new effect of activity comes in the magnetization. Magnetization is just a difference of the plus and minus kind of particles, and although at the boundaries the magnetization is 0, in the bulk we see a finite magnetization. And this happens because that in the boundaries they throw in equal number of plus and minus particles, but the two boundaries there is a difference. So, the minus kind of particles they go out rapidly, so an excess of plus remains. So, this is why although there is a zero boundary magnetization, finite magnetization is appearing. And one interesting thing is that this excess in the length that appears in the current, the length is effectively increased by some amount, and it turns out that this is exactly equal to the Milnor length. We will see later why this is the Milnor length, but it appears in the steady state also. And so, this is one kind of summary for the steady state with this particular boundary condition. Now, if you have non-zero magnetization at the boundaries, so what will happen? So, the first thing we see that the expression of the current changes. So, there is this gradient part, the density gradient drives a current, this is there, but also another component appears in the current which is driven by the boundary magnetization. So, the picture goes like this. So, you have these two reservoirs where you have equal density of particles, but the particles have different average different spin in these two reservoirs. You can construct reservoirs quite easily, I mean at least theoretically. So, what happens at one reservoir, say and Q1 plus Q0 is greater than 0, assume let us say. So, from this reservoir also you push some particles into the system, and here also you pull some particles in the same direction if both are positive. So, in the middle some current is induced. Apparently, this is like some kind of external drive. So, as if the magnetization at the boundary is acting like an external drive, but this may not be so, because if you have constant density gradient and external drive, the density, I mean if you do not have a density gradient, but an external drive only induce a current, but not any non-trivial density profile. But here we see that the density profile is first of all there is a existing a density gradient in the bulk, and also a non-monotonicity near the boundaries. So, yeah, so this we cannot really think of this magnetization as an effective drive. So, now you increase the density gradient. So, what will happen? So, say this P0 is now increased on this right reservoir. So, it will induce a current against the magnetization driven current, and at some point the current will be 0. Now, this is interesting at least to us, because you imagine a picture where you have a fixed wall, two walls, so that there is no particle current, but somehow you have some mechanism in which you give two different magnetization at the two walls, and that different magnetization will create a density gradient. It is very much like Seebeck effect, where you give two different temperature at two walls and a density gradient is created. But again it cannot be exactly Seebeck effect, because this Q0 and Q1 we do not see any associated different flux, because there is also heat flux, but here we do not know. But somehow the similarity is achieved, where these Q's here they act like temperatures, here they act like some kind of external force. And another consequence is in this case the density profile is actually constant in the bulk and the magnetization is almost 0. So, unlike the passive system where the density gradient gives the density profile, here the current that controls the density profile more, and this is the summary of this case. So, this is the steady state result of the boundary driven process. Now, we want to look at the time dependent behavior. So, for the time dependent behavior we have to solve the entire master equation. This is the linear operator with the boundary condition. So, and the general solution is you just write the steady state and you have this spectrum lambda and an eigenfunction. So, if you can solve for L, you have this general solution for all times, and from the initial condition you can get Cn. So, it is the standard procedure. However, it is usually not very easy to go through the procedure and solve for the spectrum. Here it turns out that this time dependent part, it actually solves a both side absorbing boundary problem. So, the problem just reduces to an initial value problem with absorbing boundaries at both ends, and now this is solvable. So, it turns out that there is a symmetry. The symmetry, it is like a reflection symmetry. So, a particle starting here with spin this way and a particle starting here with spin that way, these two are equivalent. So, you can use this symmetry and you can analytically solve for the spectrum, and it turns out that the spectrum is distributed in two bands. One is near 0, lambda equal to 0, yeah, okay. And this is very much passive like you see, and another band which is near 2 omega, omega is a tumble rate, and we want to look at the large time behavior in which this 2 omega band just vanishes at large times. This will be almost 0 and this will contribute. So, now we are actually looking what is the active contribution to the dynamics and all, but we see that it is very much passive like here also. So, we go at the next order and we see that this active contribution proportional to V, it comes of order 1 over L. So, now this is the relaxation for n equal to 1, this gives a relaxation behavior, and there is a non-monotonicity because at small system size the tumble rate governs the relaxation, but when the system size is large you have many tumbles, so you go to diffusive. So, but when you calculate the eigenfunction, so this is clumsy, you need not look at that, but the point is in the eigenfunction also the leading behavior is passive like and the active contribution is in the subleading order. So, apparently active contribution occurs as corrections, and if you solve for the entire spectrum you write it as a sum and you see that this active part is of the order 1 over L. However, we find that there is a n multiplied. So, at very large times you only have 1 or 2 n's contributing, but for a large system you have an intermediate time scale where you have not relaxed, but your initial 2 omega band is relaxed. So, there is some intermediate regime. So, what is happening there? So, in that regime you assume the system to be a semi infinite system, and this problem can be analytically you can actually find the spectrum, and it turns out that if you calculate this active, you sum over all the terms, you call this active term, you know the passive contribution and you take the ratio, call it R, and it turns out that in this intermediate regime, intermediate large time regime, this R that can be very large. So, actually although individual terms they contribute in a small amount, when they add up they can actually exceed the passive behavior and they can actually determine the behavior of the system. Even in the bulk, this is extends to infinity. So, in the bulk we never expect that. So, when you go far from the boundary, so there is no boundary effect, it makes a lot of tumbles, and generally there is no active kind of behavior remains and it is effectively passive, but at least in this case we find it is not so, and this is how the distribution looks like and it agrees well with the data. So, this is the characterization part is mostly complete from our side, but we have one interesting observation. So, we just show you the distribution. So, you need not follow everything here. So, it has 3 components. One is this passive component which is usual, and then there is this red one which is the new active component that gives me this active contribution, and then there is this exponentially decaying terms which is the boundary layer. So, the boundary layer is even present in the time dependent problem also, and again you see that this term in the square bracket, this is the Milnor length, and this is just to show that the diffusivity has a non-trivial consequence. When D is 0, no thermal noise, the total balance is retained of the different kind of particles, but when you switch on a thermal noise, and you can combine this part to in a more rational form. This is passive like, but there is this important new contributions which gives rise to important effects that we have just seen, and it turns out that here if you put x equal to minus Lm, it is 0. So, when you are far from the boundary, you see the effective absorbing condition, and I have to say thank you.